net angular momentum of a body remains unchanged or remains constant. That is known as conservation of angular momentum. In this case, this will be equal to dl divided by dt is equal to tau. Behind many stars, when collapsing into neutron stars or black holes, they actually spin really fast. That is because law of conservation of angular momentum exists. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with system of particles and rotational motion. So we dealt with some other quantities that were linear in sense and we converted them into angular sense. That is, velocity became angular velocity, acceleration became angular acceleration, displacement became angular displacement. So are all the terms different or is there some similar terms? Let's see. So again, in Newtonian mechanics, Newton saw the worlds in terms of lines of forces. So force was applied there, force was applied here. So what about in the case of rotational motion? Can force be applied in a rotational sense? Of course, force is applied in the rotational sense because if you get a bottle of water, let's say a Pepsi or something else, where you have to unscrew the top, what do? You press and hold on the cap and you twist the cap, which means if this is a bottle, let's say it's not a pretty bottle, well, let's say this is a bottle, and if you want to remove the cap, what do? You grab and press on the bottle and you make it spin or you rotate the cap to open it. For that, you have to apply a couple of torque. Now, what is this couple of torque? Mainly, it means that you're pinching with your two fingers, right? Which means you're applying force. When you're twisting, two forces are applied. That is, if I take my hand and try to open this, one finger is trying to give a force to one side and the other finger is trying to give a force onto the other side. So these forces will actually be equal in magnitude, but the only problem is that they are in opposite direction. In general sense, we have learned that if forces that are acting equal in magnitude but opposite in direction, they usually cancel out, giving out zero. But here there is a slight difference. Even though you are applying a force and making the bottle cap go for a spin, the force applied is in fact equal in magnitude and opposite in direction, but they are separated by a distance. They are separated by a distance. So these kind of forces where you apply a force in a rotational sense, those type of forces are actually known as forces in rotational motion, or simply we call them as torque. You might have heard torque figures for engines, bikes, cars, planes. The torque figures, the more the torque, the more peppier the bike will be. So the reason for that is because there they are counting the torque of the piston and the engine, everything that is happening inside the engine. So again, in simple sense, we can say that torque is nothing but it is a moment of force, or it is a pair of equal and opposite forces acting at a distance from each other. That is all the fancy definitions, but again, all these are fancy definitions. Let's see some definitions we are really familiar with so that you can understand the concept of torque immediately better. I have explained this topic in detail, in depth in the class. I hope you remember, but still, let's re-dive into that examples and let's see. So let's say that in an imaginary situation, my best friend Vishnu J. Prakash is living inside this particular castle. Let's say this is VJP's castle. VJP's castle. So since I disturb him all the time, what he did was he kept a big gate like this on the front of his castle. Not just for me, for everyone who wants to disturb him and for privacy. So this particular gate, how do you open a gate? Let's say if it's a normal big gate, what do? You generally go there and kick open the gate. Or you generally go there and push open the gate. But where do you push? If I'm getting into this castle, if I'm coming in a hurry and I want to open this really big gate, where do I push? So let's say that, okay, it is a gate like this. So where do I push? I come here, I push near the locks. The lock is like this. So I unlock it and I push in the center. So my question is very simple. Why are we pushing in the center? Why are we not pushing on the sides? Automatically we know that, inherently we know that in our brains, okay, pushing on the sides is very difficult for it to open. If I push on the edges, it is very easier for the gate to pop open and I can move the gate through an angle very easily. So this understanding, this inherent understanding of our brain is now mathematically represented as torque. That's the only thing. So the reason why I am not pushing at the edges and why I am pushing at the center is because of torque. So the actual definition of torque is that we can say that So the actual definition of torque can be explained as the product of linear force and perpendicular arm distance. So this is the perpendicular arms distance which is indicated by R. Okay, so this distance multiplied or taken the cross product of this particular distance will give you torque. That is a mathematical definition. That is, torque represented by a wavy T like this is actually equal to vector R cross vector F, or simply RF sine theta. It is a cross product because it is a vector quantity, that is, torque is a vector quantity. It has a certain direction. The direction will obviously be given by the right hand screw rule. So in the direction of torque, if I place my hand, the thumb will indicate the direction of movement. So that is right hand screw rule, you already know that. But again, this is the definition for torque, that is, it is the cross product of perpendicular arm distance and force applied. So force applied is obviously this one. I am applying a force at a particular angle. Okay, I am applying a force at a particular angle. Then for this to move, there should be a perpendicular arm distance. Perpendicular distance just means that from this particular point, that is the axis of rotation is here. Let's say this is the gate and this is the axis of rotation. From there to this particular line of force, if I draw a normal, then that distance is indicated by vector R or position vector R. That is known as perpendicular arm distance. And that cross product of those two will actually give you torque applied. Now, there is one more special case where torque applied can be directly equal to R into F. That is the special case when the force applied and the perpendicular arm distance, the angle between them is 90 degrees. So here the sine theta is indicating the angle. So when this is some random case where the angle is theta. Now, if I change that angle to 90 degrees, then the perpendicular distance will be making an angle of 90 degrees with the force applied. So this will be the perpendicular arm distance and this will be the force applied. So in that particular case, we'll get maximum torque. In other cases, we'll get some values which is less than the maximum value. So that is actually the mathematical definition of torque. So that is why we can actually pull back a window which is open. Sometimes when we are actually lazy, lying near the bed, we actually want to close the window, but since we have to put our hands through the grill and grab for the small thingy, that hook, to pull it back, what we try to do is that we slide to pull back the window, entire window near the hinge, but it won't come back. That is because the perpendicular arm distance, that is this particular distance, is now low, which means the entire value of torque is now low. What that actually means is that if that is not clear, I'll bring back the gate example again. If I want to smash into my friend's home, the easier way to do it will be pushing at the center, because again, the perpendicular distance, as distance increases, as this R increases, even though I apply a small force, the torque will be more because R is huge. At the same time, let's say I apply the force here. I am trying to opening this. I can't open this because obviously the distance is too small and the torque produced is also very, very small. So again, since this is a huge key to a castle, this distance must be 100 meters or something. Let's say 10 meters or 100. Let's take 10 meters. 10 meters. I'm applying a force of the maximum force I can apply. Let's say it is also 10 newtons. 10 newtons of force I'm applying. So if I'm applying 10 newtons of force here, then the net torque I can produce, assuming the angle is 90 degrees, then the net torque I can produce is 100 Newton, right? 100 Newton meters, because again it is distance times force. So it is 100 Newton meters. And now, what about in the case where I apply a force near the hinge? Let's say it is 1 meter. If I'm applying a force near the 1 meter mark, what will happen? I'll only get a torque output of 10 Newton meters. See the difference? I'm applying the same force. I'm applying the same 10 newtons of force on both the areas. So the torque is now drastically different. That is only because the distance between this point and the point where I apply the force is now different. So depending on the R value, the entire torque value actually changed, and depending on the angle also. So here I'm assuming that the angle is 90 degrees. So sine 90 is 1 and R times F will have the maximum value. So if you are far away from that particular point, more torque can be produced. That is why when you are opening doors, that twisting doors, when you are opening it, people gradually or automatically they will go to the edge and try to twist it. They won't go and grab the near center and try to twist it. And if you have ever worked with an Allen wrench or any types of wrenches, you know that the easiest way to turn or tighten a screw is to hold it at the edge and twist it. That is all because of torque. So torque is a simple thing but a complicated mechanical system because it is everywhere. Forces are everywhere. So when it is expressed in angular terms, we call it as torque. And the equation for torque is generally written as tau is equal to R cross F. But we can also assume one more equation by logic. So again, force is equal to F is equal to ma. We already know that. That is in the linear sense for Newtonian mechanics. But again, if I convert this into rotational mechanics, the rotational analog of force can be written down as, it's very simple. Analogous of force is tau. Analogous of mass, we already learned in the previous class, it is moment of inertia I. And analogous of acceleration is nothing but angular acceleration indicated by alpha. So tau is equal to I alpha. So this is the general equation, and one more equation is tau is equal to I alpha. If any mass is rotating about a point accelerating, then I can see that then the torque applied will be given by the equation I alpha. Or in another terms, I can say that in order to accelerate a mass around a specific axis, that is for a rotational motion, to accelerate that particular mass, I need to apply a torque. If no torque is applied, then there is no acceleration being produced. It's simple as that. So it's very simple, right? Tau is equal to I alpha, which is analogous to F is equal to ma. Both equations are very same. So again, in Newton's second law, we define this law, right? What was this law defined as? So Newton's second law states that rate of change of linear momentum is directly proportional to force applied. Or in this case, I'm just writing equal to F because K is a constant which is equal to 1. So I'm just writing dP by dt is equal to F. This is Newton's second law of motion in terms of force applied, that is in linear mechanics, translational motion. But now we are saying it in terms of rotational motion. So if you are doing it in terms of rotational motion, what is the difference? The only difference is that instead of the linear terms like force, momentum and all that, we use angular terms like torque and angular momentum. That is the only difference. So we can actually define the second law as the second law as the second law of rotational motion, or simply we can say that rate of change of angular momentum will be equal to net torque applied or net external torque applied. That is, in linear mechanics, it was dP by dt is equal to F, or dP by dt is directly proportional to F. In this case, this will be equal to dL divided by dt is equal to tau. So again, L is nothing but angular momentum. What angular momentum is, what is its speciality, all these things will be discussed, but understand for now, dL by dt is equal to tau is same as dP by dt is equal to F. This is linear, this is angular. That is the only difference. As a statement, we can say that the rate of change of angular momentum is directly proportional to the external torque applied. In that case, it was rate of change of linear momentum directly proportional to external force applied. Here it is angular terms. That is the only difference. So, what will be the unit retake? So, retake. So, this is second law of rotational motion. So, dL by dt is equal to tau. But sir, for this you made us prove a lot of things. You made us take differentiation chain rule and all that, and we arrived at F is equal to ma. Then how can you directly say that, okay, you have to believe me when I write this? Okay, you don't have to believe me. We'll do the same proof we did for linear mechanics and let's see what will we arrive at. So, let's see. So again, what is L? L is angular momentum, which means there should be a relation with linear momentum. The actual definition is that if a particle is represented in a rotational sense, then R will indicate the particle's position. That is, R is the position vector and P will indicate its linear momentum. Then we can actually say that that particular rotating particle relation with its linear momentum can be expressed as L is equal to vector R cross vector P. Okay, this is how we express angular momentum. So, to arrive at this particular result, we have to have one thing. To arrive at that particular result, the one thing we need is proof. So, the proof is that we are going to derive whatever the law states. So, the law states, what is the law state? Rate of change of angular momentum is directly proportional to net torque applied, right? So, rate of change of angular momentum dL divided by dt is equal to or directly proportional to tau. So, we do know that L is equal to generally R cross P. This is the relation between linear momentum and angular momentum. Angular momentum is equal to R cross linear momentum. R is nothing but the position vector indicating the particle which is having linear momentum P. So, if I substitute this equation here, then I can say that d of r cross p divided by dt is directly proportional to tau. Or again, I am taking it as equal to tau into k, and k is nothing but 1. So I am taking it as the same derivation we did for that particular side. That is, in the linear sense we are doing here. The only difference is in the left hand side. So r cross p divided by dt is equal to tau. Okay, where k is equal to 1. Now, how do we differentiate this particular quantity? Again, the simple thing we do is that we apply chain rule. So the chain rule states is that we take this quantity, keep it outside of the differentiation symbol, and then we differentiate whatever is remaining, plus now we keep the second quantity outside and differentiate whatever is remaining inside this particular quantity. So this can be written down as, first we take the first quantity, keep it outside and differentiate whatever is remaining, dp by dt, plus now we keep the second quantity outside, which is momentum p, and differentiate whatever quantity is remaining inside, so dr by dt. So this is how this result will look like. Now this will be equal to torque applied tau. Wait, I'll write this all neatly once. Now we arrive at this particular result where r into, that is position vector r into dp by dt plus momentum p into dr by dt. Now what is dp by dt? We already know from linear mechanics that dp by dt is nothing but rate of change of momentum is equal to force applied, that is F. So we get this particular equation as, so before this, again remember there is an operator here, that is cross. So this will be r cross dp by dt plus p cross dp by dt. Don't forget about the operator symbol. So you can write r cross dp by dt plus p cross dr by dt. So again then we can write this equation as r cross, that is vector r cross dp by dt is nothing but F. So r cross F plus p cross, what is dr by dt? Rate of change of displacement, because r is nothing but a position vector indicating position. Rate of change of position is nothing but, rate of change of displacement is nothing but velocity. So we can write this as velocity. So this will actually be equal to r cross F plus p cross v. So again, r cross F is nothing but torque. So we can say that tau plus P is equal to, okay, now P is equal to mv, right? Linear momentum is equal to mass times velocity, mv. So we can say that, okay, this is equal to mv cross v. What is v cross v? V cross v is equal to 0, right? V cross v is equal to 0. Why it is 0? Okay, if I take two vectors, let's say this is vector A, and if I cross it with the same vector, what will happen? If I cross it with the same vector, it means the angle between them is 0 degrees. If I take 2 points in this line, the angle between those 2 points is 0 degrees, which means that A cross A will be equal to A into A or A square sine theta. Theta is nothing but 0 degrees. So sine 0 is 0, a square into sine 0. Here it will be v square into sine 0, which is equal to 0. So this entire term will be equal to 0. And the only remaining quantity is tau. So we stated that we started from dl by dt. The real way to do this particular derivation is that we start from, okay, dl by dt. We don't know what is rate of change of angular momentum. So we start from dl by dt. dl by dt, what is L? L is nothing but r cross p. So r cross p in of d by dt. So again, we applied the chain rule and said that, okay, r cross dp by dt plus p cross dr by dt is the result of this particular derivative. And again, we know that dp by dt is nothing but f and dr by dt is nothing but velocity. So we can write r cross f plus p cross v. We get this particular result, and p is nothing but mv. R cross f is nothing but tau. So tau plus m into v cross v, and v cross v is 0. So we get the final result as tau, which means dl by dt is now equal to tau. Right? Now is equal to tau. That is the final result. So we get rate of change of angular momentum is equal to net external torque applied. So what if I don't apply any external torque? If I don't apply any external torque, what will be the result? Rate of change of angular momentum will be 0. Again, if I am applying 0 torque, then I can say that tau is equal to 0, which means dl by dt is equal to 0, which means L is equal to a constant value. Right? L will be constant. Again, remember dl by dt, rate of change. If no torque is applied, angular momentum is not changing. If angular momentum is not changing, rate of that change will be 0. It is not changing, dl is 0. So we can say that L is a constant. dl means change. Position 1 minus position 2. If position 1 and position 2 are same, then only we get 0, which means L is not changing. It is a constant value. Then we can say that dl by dt is equal to 0 implies L is a constant. This particular thing is known as law of conservation of angular momentum. When there is no external torque applied, or in the absence of an external torque, the net angular momentum of a body remains unchanged or remains constant. That is known as conservation of angular momentum. So conservation of angular momentum states that in the absence of an external torque, the net angular momentum of a body, remains constant. You can think it logically also. That is, dl should be 0. How can dl be 0? dl signifies small change. If there is not even a small change, it means L is not changing. L is a constant value, which means angular momentum is a constant. So here I can say that, okay, L is equal to constant. What that states is that, what it means is that, okay, angular momentum is conserved. So this is the proof for conservation of angular momentum, that is L. So this is the proof for conservation of angular momentum. So you write the statement, in the absence of an external torque, the angular momentum is conserved, or simply dl by dt is equal to 0, which means L is a constant. That's it. So we already learned what angular momentum is. Angular momentum is nothing but L is equal to, it's a vector quantity, it is R cross P. It is R cross P and its SI unit, I am leaving it to you because again you have the equation. This is a length quantity and this is momentum in linear terms. You can figure out the SI unit, it's very easy. So again, this is one way of expressing angular momentum. This is the general sense. And if you want one more method or if you want one more equation, we can say that, okay, I know that linear momentum is expressed as mv. So from that, how can I figure out angular momentum? So okay, I know, because in linear sense, if P is equal to mv, in angular sense, I can say, okay, it is angular momentum L, and instead of mass, I can write I, and instead of velocity, I have to write angular velocity, which is omega, right? L is equal to I omega. That is angular velocity. Now, what does the second law states? The second law states that, the second law in rotational motion states that rate of change of angular momentum is equal to net external torque applied. So instead of this particular equation, I am going to put in this particular equation, that is L is equal to I omega. So it just means that moment of inertia times angular velocity or angular frequency. You can also say in terms of frequency also, it's fine. But the meaning is that, okay, a rotating body will have angular momentum and that will be equal to moment of inertia, that is the reluctance of that particular body to go for a spin times how fast it is rotating. That two quantities will determine angular momentum. But for you, the equation is only enough. So you can imagine it in this way. Okay, this is the translational analogous to angular momentum. So in the rotational sense, I can say that, okay, instead of P, it will be L. Instead of mass, it will be moment of inertia. Instead of velocity, it will be angular velocity. So like that, you can just imagine. Now, again, if I differentiate those particular quantities, I can say that this will be equal to I omega divided by dt, which is equal to tau. Again, here, are there any constant quantities? Of course there is. There is a constant quantity, that is I. I is written down as moment of inertia, or simply it is analogous to mass. Mass of a system or reluctance of a system to spin is not going to change over time. If I keep a rock here for 5 minutes, after some time it is not going to change its mind and say, okay, I'll rotate faster from next day. No. So I is a constant which comes right outside, and the only remaining quantity is d omega by dt. Omega is nothing but angular velocity. If I take the derivative or rate of change of angular velocity, rate of change of velocity is acceleration. Rate of change of angular velocity is angular acceleration. So I can write this as I alpha, which is equal to tau. So this is where the equation actually comes from. Later I just wrote down, okay, by using logic I can say F is equal to ma. So in this sense it will be I alpha. I moment of inertia instead of mass, angular acceleration instead of acceleration. So this is how you actually get the equation. This is the right way. If I ask you to derive this, you have to use this particular format and not say, okay, by applying logic. You have to apply this particular logic and this particular equations and steps in order to prove that. But again, I just wanted to show you, this is where the equation comes from. So if I give you moment of inertia of a body and velocity in terms of, let's say, vector notation, you can just take the derivative and you will find what is torque applied. Or if I give you angular acceleration and torque applied, then you can automatically figure out what is the moment of inertia of that particular body. So again, the equations tell beautiful stories if you can actually listen to it. So again, I am going to bring back the concept of conservation of angular momentum for a brief moment. So this actually is an intriguing property. If you can actually do several experiments with that. You might have seen in YouTubes and all that if you spin a cycle tire and hold it by a rope, the tire actually spins like this and rotates about. So the reason for that is because conservation of angular momentum. because tau is equal to dl divided by dt. Angular momentum will always chase torque. That is the actual, or that is the logic behind that particular experiment. But again, in the absence of an external torque, if I am not applying any force from the outside to spin that particular body, angular momentum of a body should remain constant, which means what it actually means is that if there was a body like this, okay, let's say this is Earth. Earth is now rotating about its axis like this, rotating about its axis at, let's say, velocity of omega, angular velocity omega. It is now rotating. Now, if I change its density, that is, if I am changing the volume of that particular sphere to make it smaller, what will happen to its velocity? I am not applying any external torque. I am magically just shrinking that sphere. So what will happen? If next day, that is tomorrow, the Earth suddenly lost a bunch of its volume and not its mass, just the volume, what will happen? So the thing is that you can also actually try this with homemade experiments if you can. So if it loses that particular volume, it means that the angular momentum should be conserved. Again, momentum or angular momentum L is equal to I omega. I is not changing. Mass of the system is not changing. Right? Mass of the system is not changing. Mass distribution is not changing. The only thing that can change is omega. Mass of the system is remaining constant, which means mass of the system is not going anywhere. And now, unfortunately, by law of conservation of momentum, I said that there is no external torque applied. If there is no external force or torque applied, then and mass can also not be changed, then automatically the only quantity that can be changed is omega. So to conserve this angular momentum, the body has to now spin faster. Now, the practical and vivid example you can see is in Olympic sports. That is, you might have seen ice skating or figure skating. So when they go for figure skating, they will gradually go like this, they'll slide, and while they are spinning, they'll spin like this, and while they are jumping and spinning, they'll fold their arms and spin. Right? Instead of spinning like this, they will fold their arms and spin. And it just so happens that when they fold their hands, they seem to spin faster. You can try this by sitting on a swing, spreading out your hands and trying to spin. At the same time, when the spin is going on, fold your arms and you can see that you will spin faster. The reason is because of angular velocity increasing, or simply angular momentum being conserved. Because again, when you're spinning like this, what happens? Your velocity is low. When you fold in your hands, by law of conservation of angular momentum, your mass is not changing. The only thing that can now change is angular velocity. So you have to spin faster. That is actually the reason behind many stars, when collapsing into neutron stars or black holes, they actually spin really fast. That is because law of conservation of angular momentum exists. So it is a beautiful concept. You have several visualization concepts everywhere all over the internet. You can actually take a look at it. So I hope you have understood about what is angular momentum. And remember, this L is equal to R cross P. Sir, is this the equation to use, or is this the equation to use? Are both equations different? It's a common question we get all of the time. So again, both these equations are basically the same. This is for the general definition where I use a point particle. That is, if I take a point particle in space and say that, okay, this point particle of, let's say, mass m1 and having velocity v1 is indicated by having a linear momentum of p, then I can say that I can indicate the position vector as r. Then I am saying that, okay, r cross p is the angular momentum of that point particle. Now, if I am saying it for a rigid body, what is a rigid body? Again, a rigid body is something in which distance between the particles do not change with time. Okay, you have to know what is a rigid body. I have explained this in the class also. Rigid body is nothing but the body in which the distance between the mass particles do not change for small forces or with respect to time. That is, if it changes with respect to small forces, it is called a plastic body or elastic body. And if it changes completely with respect to time, then we can call it as a liquid. So again, if that does not happen, if I hold this pen for a really long time and slightly twist it, is it deforming? No, that is because this is a rigid body. In a rigid body, distance between the particles do not generally change. So that is known as a rigid body. For that rigid bodies, you can actually use this particular equation, that is L is equal to I omega. For point particles, you can use the equation R cross P. There is no way you're going to use point particle equations and all that. You'll basically get this particular equation I omega, but I just wanted you to know. And the last thing I wanted to let you know was what is radius of gyration. Basically, what radius of gyration tells is that if we have an axis of rotation and a particular distance away from the axis of rotation, there will be a point where all the mass is supposed to be concentrated, right? Imagine that all the mass of a body is supposedly concentrated in a single point. Okay, it is known as center of mass. Okay, it is known as center of mass. We'll discuss about center of mass very soon, but again, the distance from that particular axis to that particular point is the measure of radius of gyration, basically ensuring that the spin is proper. So if a body is spinning, it will have a reluctance or it will have a tendency to go in that particular spin state only. It will have a reluctancy to change that particular direction. The measure of that is actually known as radius of gyration, and it is indicated by the letter capital and it is indicated by the letter K. So the equation is the only thing we are actually concerned about. But again, I'll tell you in detail what is radius of gyration if it demands. But for now, understand that radius of gyration is nothing but K is equal to root of I by M. So radius of gyration is nothing but K is equal to root of I by M, where I is the moment of inertia and M is the mass of the body. This particular relation will give you what is radius of gyration. If you want more examples, I'll try to include more examples in the next class. But for now, this is the only thing we need from a numerical standpoint of view. So I hope you have understood everything about what is torque, what is angular momentum, what is the specialities of angular momentum, why athletes close their hands in order to spin faster, why large bodies suddenly being shrunken spin faster. That is simply because angular momentum is conserved. Obviously, if there is no change in mass and no external torque being applied, then the body has to increase its angular momentum. That is how the body will actually spin faster. So I'll meet you all in the next class with some kinetic and potential energies. Until then, thank you.